Hey everyone, this is Saptarshi here and I welcome you to a video tutorial on activation functions. I'm sure you already know how important this is to learn activation functions for neural networks. Let's first look at what is activation function. Okay, so here you have a biological neuron and you have the artificial neuron counterpart, right? And it is schematically represented like you have several inputs x0, x1, x2 coming to this neuron or this computational unit. They are getting multiplied by some weights, okay, which are called as synaptic weights and goes to the cell body for aggregation. Then a function is applied on this, okay, and some output is produced. So that output, it goes to this action and are available to other neurons, okay. So that's how you know that this biological neuron is equivalent with a mathematical model of neuron. So what is the role of activation function over here? So it basically controls that based on the stimuli it receives or based on the input it receives, when it will react, okay, when it will fire and how much, in what magnitude it will fire, okay. So this is controlled by the activation function F. So this is your activation function, and this activation function can be of several types. Based on the types, the way the neuron will work actually dramatically changes. Let's start by looking at the most primitive activation function. So here what happens is you have the linear aggregated input over here and you have the corresponding output. So you can see the output is 0 and 1. So immediately we can conclude that this can be used for a binary classification problem. Okay. However, you can also notice that the rate of change in y with respect to z is 0 in this case, in this region. Okay, there is no change actually. Similarly, there is no change also over here, and the change is almost infinite in this region or for this value. Okay, so that brings us to a trouble. What is the trouble? If you remember that in a neural network, the weights that we just discussed, W0, W and W1, W2 are found out through an algorithm called as gradient descent. And gradient descent depends on derivatives, okay? But here you see that this function doesn't have derivatives. So we cannot use gradient descent. We can use it for single layer, can find the weights through perceptron learning algorithm. But when we move to multiple layers, where you need to use gradient descent and back propagation, this activation function will not work. So one of the key properties of an activation function is it should be differentiable. The derivatives you should be able to find. So next we move to something called as a linear neuron. So now the functions that we are going to discuss are differentiable. So we are going to plot both the things. In the red arrows, we are going to plot the actual function, and in the blue color, we are going to plot the derivative. So one of the things that we quickly see is that it has a continuous output coming in, so it is suited for linear regression. It is differentiable. However, the gradient is unaffected by value of the input because you see the gradient is constant over here. Gradient is actually 1. Okay. So one of the problem, okay, with such linear units is that when you are trying to find out a decision boundary like this, okay, you can easily find that out. However, if you have to find a decision boundary like this, you can stack how many ever layers you want to, you cannot come with a decision boundary like this. All right. So second property of activation function is that it should introduce non-linearity. This non-linearity actually allows neural networks to understand, find, discover complex non-linear structures or patterns. Okay, all right. Let's now look at sigmoid function. So this is also a very famous function, very popular in the literature. So this is the original value. Original value of the function is between 0 and 1, okay, and the derivative is also between 0 and you can say 0.25. All right. So what are the characteristics of this particular activation function? So it is differentiable, right? Perfectly suits binary classification. If you look at this curve, it looks completely like logistic regression, right? So it suits binary classification, and it is not like your hard binary classifier of step function. It is a soft classifier because it can predict probability. Okay. However, one thing if you notice is that the gradients in quite a lot of the region, right, the derivatives are very, very close to zero. So, any neural network learns the weights through gradient descent. Gradient descent is dependent on derivatives, right? So, if the derivatives are very, very small, the neural networks will also, learn the weights very, very slowly, all right? So this problem, we call it as a saturated gradient problem, all right? So also there is another problem, this was not centered around zero. If you remember, the value of our sigmoid neuron was between 0 to 1, right? So it was never negative. And this brings another kind of problem, which we call as not centered around zero problem. So let's understand this problem with more details with this example. Okay. So we are here concentrating only these two weights, W311 and W312. Like any gradient descent weight update step, they are updated using this particular equation. Neta is your learning rate and this is your derivative. Now let's look at how these derivatives can be calculated. So we are not much interested at the calculation of the derivative. However, if you follow the calculation, you will quickly note that there is one term which is changing, okay, which is nothing but or which is constant for both these weights, and there is one part which is different in these two weights, okay. So which is the activation function H21 in case of W311 and H22 in case of W312. All right. So now if you think little bit, we'll realize that, if the common part is positive, your H21 and H22 will be always positive because that is what is the nature of your sigmoid function. So the overall value will also be positive. Okay. And if this common part is negative, then also the overall value will be negative. So what is the problem with that? The problem with that is that all the weights that are going to a particular neuron, okay, going to a particular hidden neuron, their change in direction will always be in the same direction. Either all of them will be positive or all of them will be negative. Again, what is the problem with that? The problem is, if you remember in gradient descent, when we try to, draw contours, we try to take many random movements, right? Okay. However, when we are using a sigmoid function, some of the quadrants are not allowable to be reached, okay? Where, one of the weights is negative and the other is positive. So either both of them are positive or both of them are negative. So as a result, the optimization is not as good as it should be, right? So there will be a zigzag tendency, there will be slower convergence. Okay, so now let's look at another function which is very similar to a logistic function. You can only feel that this is little more stretched out. Okay, so it is not anymore from 0 to 1, but it is between -1 to +1. So this is nicely centered around 0, doesn't suffer from the problem that we just discussed. There is also another thing. If you look at this gradient, okay, so this gradient here is much steeper, okay, compared to what we had in our logistic or sigmoid function. So the learning happens for a more wider area, resulting in faster convergence. So if you compare, you can see over here, okay, that it is much less steep here and it is quite steep here, So learning is much faster. Now let's understand another important problem which is called as vanishing gradient, and do not worry too much about this notation. So what we are trying to tell you is that this is a multi-layer perceptron with different activation functions, okay, and when we try to find out these weights, we find the chain rule. The chain rule is applied on the error that comes from the actual value and the predicted value. So it can be written in something of this form. Okay. So one of the things that we see is that this is a multiplication of multiple derivative terms. So if you remember our back propagation lecture, so these derivatives actually are back propagated, and if there are n terms that are participating in the derivative calculation over here it will be n plus 1 term at least. Okay, so as you move from layer to layer, these components grow up. Now if you remember your sigmoid function or Tanh function, so there is quite a lot of area where the gradients are very small. So if you multiply many small units, what will happen? They will very quickly go to 0, or they will try to get vanished, right? So this gives a problem that though the layers which are closer to the output, the derivatives with respect to error will be something and they will still learn, but as you move away to the input layers, the gradients will be very small, and with the rate it will learn will also go down, making it very unsuitable for neural networks with deep or lot of layers. Okay, so there you get a function called as ReLU. So this is your actual function, okay, so which is linear when x is positive and it is 0 when x is negative. Okay, and the derivative exists in this quadrant, the derivative doesn't exist over here. All right, so what is the advantage of this? First of all, you do not have this vanishing gradient problem anymore, okay, because you see the gradients are not small anymore, right? And here the calculation happens much faster. So in our later slides, I will give you the mathematical form of the activation function, so you'll realize that both your sigmoid and your Tanh or hyperbolic activation function needs much more complex computation. Okay, and another advantage is it gives sparsity. So what we mean by that? So basically, any machine learning or deep learning model, the more the layers, more parameters you have. More parameters you have, more prone it is for overfitting. Okay, so here what happens is that some neurons which are receiving a negative input, their gradient will be 0 and they will not be participating in that particular forward pass or that particular backward pass, right? So that gives kind of sparsity, and if you have sparsity, your model will be less prone to overfitting. Okay. However, it turns out that when your neurons are in this zone, okay, it is very difficult that they will come out of here, right? That their gradient will be negative or 0 and they will stay there. So you call such neurons as dead neurons. But before that, let me ask you one question that we told you that one of the properties of the activation functions is to introduce non-linearity, right? So ReLU, here it is linear, and here you can say it is maximum, it is quased or suppressed, right? So how this can probably give you a non-linear complex boundary? Okay, the answer or the intuition remains in your piecewise linear regression, right? So if you remember, if I want to find a decision boundary, and if I somehow allow to make two lines, right? So now these are no longer linear. So if I further split, okay, like this, then this, okay, so I can come to a much more non-linear boundary. Okay, so there, ReLU can really not compromise with the non-linearity part of the neural networks. Okay, to solve this dead neuron part, we have something called as leaky ReLU. So what we do over here is we don't make the function completely zero. Rather than that, we have a very small value over here. Okay, now maybe here you have y equal to 0.01 x or 0.01 j. So resulting in a very small derivative. So in this case, this will no longer result into dead neuron. Okay, calculation happens much faster, as was in the case of ReLU, and it can solve this problem of dead neuron. And there are some variants of this, leaky version of ReLU, which has a slope of 0.01. You can add a parameter rather than the hard-coded value of 0.01, or you can also try some exponential component of this, ReLU, but only in the negative part of the input. Okay, all right. So, however, as the gradients here are like kind of bounded, it can go up and up and up. There can be one problem which is called as exploding gradient. Okay, like vanishing gradient. So here you can have different derivative components which are more than one, and if you multiply a lot of them through a deep layers of neural network, the gradient can explode, right? So a very simple, strategy to solve this is through gradient clipping. So where, what you can do is you can just put a function where it will be clipped like this. Okay. Uh, so now let's look at the mathematical functions. Okay, so intuitively you have understood all of this. However, just look at sigmoid function and Tanh H. So why I was telling that computation of this were difficult or are time consuming, especially if you are using them in lot of layers. All right. So ReLU we have already discussed, and leaky ReLU also we have discussed. So one of the things that you can notice is that for sigmoid and hyperbolic tangent, the functions are bounded function. However, please note that for ReLU and leaky ReLU, both the function as well as its derivative are not bounded. Okay, all right. So now let's look at softmax. So you may not really put that in activation function. It is just a mechanism to produce output for multi-class classification problem. Okay, so not binary classification, it is multi-class classification, and it can be used at the output layer. So essentially, if you have n output layers, then or n output classes, you can use a softmax, and that will give you a probability vector. Okay, so which is kind of probability of each of the classes. Okay, so here you can see that the green class has the highest probability. So, and of course the probability across all the classes will add up to 1. All right. Now let's quickly look at a summary of all the activation functions. So you start with step function. The application is single layer binary classifier. It cannot extend to multiple layers as it is not differentiable. Then we saw linear activation, which can be applied for linear regression. However, it cannot find complex boundaries, and the gradient is also constant. Okay. Then we move to sigmoid. So this can be used for shallow network. Okay, if the network is not so big, then you can use it, and also you can use it for deep neural output layer for binary classification, but at the output layer. The problems were that it was not zero centered, suffered from the problem of gradient saturation, and also had this vanishing gradient problem. So Tanh H has same application as sigmoid. However, it suffers less from gradient saturation, suffers but suffers less, and also has the vanishing gradient problem, but doesn't suffer from the zero centered problem. Next, we move to ReLU. So it can be used in all hidden layers. However, it has the problem of dead neuron, and the derivatives are unbounded. Okay, leaky ReLU actually solved this problem of dead neuron, but the derivative still is unbounded. Okay, so In this video tutorial, we try to give you a good overview, good understanding of different activation functions. Hope you have learned something from here. I request you to put your question in comment sections, and if you have found this video helpful, please give your like and subscribe to our YouTube channel. Thank you so much guys for watching this video.